Welcome back to this next video in which we are discussing continuous functions between two topological spaces. Okay, so we've seen now that the definition of a continuous function f between a topological space x with the topology tau x and a topological space y with the topology tau y is a function for which it is the case that if you take any open set that's in the topology tau y, that the pre-image of that open set under the mapping f, so all the points in the domain which are mapped onto that open set in the codomain by the function f, that subset of the domain set capital X must be an open set in the domain topological space, i.e. it must be in tau x. Okay, so this is a very abstract definition, and what I want to do is try to motivate this definition. I want to use my informal intuition about what a topology actually does to a set in terms of defining which elements are next to which other elements in the set, to try and motivate this definition. Okay, right. So in the previous video, what I said then is that the informal intuition for what a topological space is, for what a topology does to a set, is that it tells you which elements of the set are next to each other. And in fact, I think I'll draw out a fresh picture down here. Okay, so let's have our set capital X, which has this topology tau x on it. Okay, and what we can do is informally, the intuition we can have for this is that we can use this topology tau x to define which elements of this set capital X are next to each other in the set. Okay, so the way that we did it, remember, is if we have one little point which we'll call x and one point which we'll call x bar here, so 2 points, 2 elements, in my set capital X, I would say that I was going to draw a line in between them and say that those 2 points were next to each other if it was the case that they had to appear as a pair whenever one of them appeared in a set that was in the open, the topology on this set X. So I was going to draw a line and say that the two were next to each other, they were close to each other, if it was the case that for all the subsets that are in the topology tau x here, these two elements, if they appear, they have to appear together. So never in any of these sets do you have just one in isolation. You always have the two together. Okay, so using that intuition, that what this allows us to do is form a meshwork basically of elements which are next to each other on this set here. Okay, so to decide what's close to what then would be the intuitive definition of a continuous map from a topological space X to a topological space Y over here? Okay, well for me the intuitive definition would be to say that if we look at the image of these 2 points in the codomain set over here, Y, so if we look at f of x and f of x bar, okay, so to make this utterly explicit, our point little x here is mapped onto f of x here, and our point little x bar is mapped onto f of x bar by the function f here. Okay, so to colour this in, here is our set capital X here, and here is our set capital Y. The intuitive definition of continuity for me would be that we want the image of these 2 points to be connected, to be next to each other in the codomain. Okay, so we want these 2 points here to have a little line drawn between them if they have a little line drawn between them here. Okay, so that is the intuitive picture of what continuity is going to be between topological spaces in terms of my informal intuition about what a topology does to a set. Okay, and what I now want to show you is how this is equivalent to this. Okay, right, so how can I do this? Okay, well what I want to do is I want to show that these two, using my informal intuition, would always be together in any in any subset that's in the topology on Y, if these two are always together in any subset on the topology of X, tau X here. Okay, so what I want to say is f of x, let's say, is in some open set, capital V, which is an element of the topology tau y. So V is going to be an element of the topology tau y. Okay, so I've just said let V here be an open set, i.e. a set that's in the topology tau y. Okay, and suppose that f of x, this point here, is going to be in that open set. So what do I now need to show? I want to show that f of y here, not f of y, f of x bar here will also be in that open set. Okay, because if it was always the case that f of x bar had to be in this open set as well, if f of x was in it, then I would draw a line in between these two, and I would say that they were next to each other. Okay, so how am I going to prove this then? Well, what I'm going to do is use the fact that we're going to say that this is true. Okay, so I'm supposing that this abstract definition is true, and I want to show that this more intuitive definition is then true if this is true. Okay, so if this abstract definition then is true, then the inverse image of this open set V is going to be an open set in my domain topological space. So the inverse image of V is an element of tau x. Okay, what else can I say about f inverse of V, the pre-image of the open set V under the map F? I can also say that the element little x is going to be in there. Okay, so the other thing I can say is that x is going to be an element of the pre-image of this set capital V under the mapping F. Okay, and the reason I can do that is I assumed that f of x, this element here, was in my open set V, and that means that x has to be in the inverse image, or the pre-image. I'm sorry, I keep moving between terminology. Pre-image and inverse image, they're the same thing. Okay, so if f of x is in the open set V, which is an open set in Y, then of course x is going to be in the pre-image of that open set in the set capital X. Okay, right. So what can I now say? Well, I can say that because this is an open set in X, and I assumed that X and X bar, I could draw this little line between them, that means that X bar must also be an element of this open set. So X bar must also be in the pre-image of the set capital V in the topological space X. Okay, so I hope you understand why I'm saying that. Remember what I'm trying to prove. I'm trying to prove that if x and x bar have a little line drawn between them, if they're next to each other in this domain topological space, that the images of those points under the map F, f of x and f of x bar, that they'll be next to each other in the topological space Y, if this definition of continuous is true. Okay, so I'm trying to associate this abstract definition with this intuitive definition of continuity. Okay, so I have now said that, okay, we've taken an open set that contains f of x in the codomain topological space Y here, okay, and we've then said, okay, because this is true, the pre-image of that open set must be an open set here, and x has to be an element of that open set because f of x is in the set capital V here. Therefore, because these two, I've drawn a line between them, they would have to both be in this open set together. So x bar, therefore, is also going to have to be in f inverse of V. But if x bar here is an element of the pre-image of this set capital V, then what that is going to mean is that f of x bar must be in V. Okay, just by definition, because remember, the pre-image of a subset V of the codomain is just exactly all the elements in the domain which are mapped into that subset of the codomain. Okay, and therefore f of x bar has to be in our subset V. Okay, so what I have done is I've said, okay, we start off with an open set that contains f of x. If this is true, and it's also true that these two are next to each other in our informal intuition of what the topology means over here, then I can show that f of x bar is also going to be in this open set where we had f of x. So I've just shown you basically that any open set in the codomain topological space that contains f of x has to contain f of x bar if this definition is true and if those two were connected to one another, were next to each other in the domain topological space. So indeed, this is the informal intuition for what a continuous function actually means between two topological spaces. It means that elements of the domain set that are next to each other are going to be mapped onto elements in the codomain set that are also next to each other, using this informal intuition of what a topology actually does to a set, i.e. that it defines which elements of the set are next to each other. So that's the informal intuition for what a continuous function actually is. Okay, right. What I now want to do is talk about two really important theorems or facts, whatever you want to call them, about continuous functions. And the first one that I want to address, look at, addresses a point that a lot of people get confused about, a misconception that a lot of people have, and it is about the inverse of a continuous function. So people often think that if the inverse of a continuous function exists, that it must be continuous as well, that the inverse of a continuous function will be continuous. So suppose we have a function f which is bijective, so injective and surjective, one-to-one and onto, and therefore will have an inverse. Is it the case that if that function forward is continuous, then the inverse function is going to be continuous as well? Well, the answer is no, and the way I want to show you this is by giving you a counterexample, a really simple counterexample. Okay, so let's do an example here, and this will also help to firm in the concept of a continuous function. Okay, so we're going to take a very simple example. So we're going to take very simple sets. So I'm going to work with the set that just contains 3 elements. Okay, so our set capital X here is going to be the set that just contains 3 elements, and I'm going to pick as my codomain set the exact same set. Okay, so the set that contains 3 elements again, like so. Okay, so my domain and codomain are exactly the same as far as sets are concerned, but now what I'm going to do is make them different to one another. I'm going to make them different topological spaces. So I'm going to equip each of these sets, the domain set and the codomain set, with a different topology. Okay, so the way I'm going to do this is initially I'm going to equip my domain set here with a topology which is going to be the discrete topology. So its topology is going to be the power set of X. So it's going to be every possible subset. So to write this out explicitly, you're going to have in here the empty set, and I'll just move this up a little bit. Okay, you'll have the empty set, you'll have all the singleton sets, so you'll have 1, the set containing 2, the set containing 3 here. Okay, then you'll have the pairs, so you'll have the set containing 1 and 2, the set containing 1 and 3, and finally the set that contains 2 and 3, and then finally you'll have the entire set, which is the set containing 1, 2, and 3. Okay, so here is the topology that I'm going to equip the domain set with to make it a topological space. And we know that whenever you have any set and you equip it with this discrete topology, a topology that's equal to the power set of that set, it always makes a topological space. So this is indeed a topological space. Now, for the codomain here, I'm going to equip it with the chaotic topology. Okay, the topology that only contains 2 subsets, and those are the 2 it has to contain. So the empty set, and then the entire set, so the set containing 1, 2, and 3 will be there. Okay, so 2 very different topologies. Okay, now I'm going to come up with the most simple function you could possibly imagine then. And it's going to be the function that maps everything onto itself. So 1 will go into 1, 2 will go to 2, and 3 will go to 3. So the identity map as far as set theory is concerned. Okay, so what we're going to ask is this function continuous? So is this function in the forward direction continuous? Okay, so let's just apply our abstract definition. So we need to ask, is it the case that for any open set that you take in the codomain topological space, that the pre-image of that in the domain topological space is also an open set. So we'll start off with the empty set. What is the pre-image of the empty set? Okay, well that's going to be all elements in the domain topological space that are mapped onto the empty set. Well, none of the elements in the domain topological space are mapped onto any of the elements in the empty set because there are no elements in the empty set. And therefore the pre-image of the empty set is just going to be the empty set. But of course that is an open set in our domain topological space, so bravo, that's worked very well. Okay, now the only other one then that we need to check is this only other open set here, which is the entire set. So the entire set 1, 2, 3, what's the pre-image of the entire set 1, 2, 3? Well, of course that's the entire set, because the entire set over here is mapped onto the entire set over here. Okay, and again, this entire set is an open set, so indeed this is a continuous function. Okay, now what I'd like to go back to is my intuitive view of what it means for a function to be continuous, to try and explain why this function is going to be continuous. So, what's the intuitive view then of the topology here, the discrete topology on this set 1, 2, 3? Okay, so I want to try and put connections between the elements of this set that are next to each other. And remember, the way I will do this is I'll draw lines between the elements if they always occur in pairs whenever they occur in a subset that's in the topology. Now, let's ask, shall we connect 1 and 2? Well, no, we can't do that because look, here is the singleton 1, so 1's on its own without 2. So it's not the case that in all of these subsets that are in the topology, 1 and 2 have to appear together when they appear at all. Okay, because 1 is appearing on its own here without 2, so that's already broken it. So I'm not going to link 1 and 2. And of course the arguments extend for 1 and 3 and 2 and 3 as well, because in fact we have all of these singletons. So in fact, as soon as you have all the singletons here, it becomes it becomes a catastrophe. You can't say that any of these are next to each other, and this is indeed why this is called the discrete topology, because basically nothing is connected to anything, basically. Everything is discrete. Everything lives on its own and is friendless in the world. Okay, so this is the discrete topology here, so nothing is connected with anything. Now it's the exact opposite when we have the chaotic topology. Okay, so let's ask, which elements shall we connect together here? Which elements are going to be next to each other? Well, in fact, everything is going to be next to everything else. So we'll draw a line between 1 and 2, a line between 2 and 3, and a line between 1 and 3. Everything is next to everything else, because the only two open sets that we've got here are the empty set and the set 1, 2, 3. So it's always the case that in any set, any open set, where one of these elements appears, it appears with all the others, and which is this entire set here, and therefore it is the case, for instance, if we take the example of 1 and 2, whenever either of those appears in an open set, they have to appear together, because each of them only appears once in this entire set here, and they do indeed appear together. So in the only open set where 1 appears, it appears with 2, and in the only set where 2 appears, 1 appears with it. So that's perfect, we can draw a line between them. And the same argument holds true with regards to 2 and 3 and 1 and 3 as well. So we will connect all of them, they are next to each other, they are close to each other. Okay, so is this then going to satisfy the condition that all of the elements that are connected to each other here are going to be connected to each other over here? Well, it does, trivially, because none of the elements here are connected to each other, so there's nothing to check. You don't need to worry about whether they're connected to each other over here. Now note, my definition of continuous did not say that it had to be the case that elements that were not next to each other couldn't end up being next to each other here. All it said that it was that if two elements were next to each other over here, they had to also be next to each other over here. None of them are next to each other over here, so we don't have anything to check. It doesn't have to be the case that elements that are not next to each other over here cannot end up next to each other here. So this is fine, basically. It doesn't matter that we're taking elements that aren't next to each other and putting them next to each other in the codomain. Okay, it's fine that way round. Now, imagine doing the inverse function here. Imagine going the other way, the inverse function, which is still the identity map as far as set theory is concerned. Okay, so now turn the arrows the other way. So imagine the arrows are going this way now, from this topological space into this one. Well, hopefully you will see straight away that this isn't going to be continuous just from my intuition here. Because look, all of these are connected to each other here, but they're not going to be connected to each other over here, so it's going to fail this. But let's see rigorously why it's not going to be a continuous function. Well, quite simply, we have to check all of these open sets. We have to check their inverse images in the Y topological space here, and make sure that they are open sets. Well, quite simply, let's take one that spells catastrophe here. Let's take the set that just contains 1 here. And of course the inverse image of 1 is just going to be 1, and that set is not an open set in the topology on Y. So indeed, already we have disproven that the inverse function is going to be continuous. Now note, this is a bijective function, okay, easily bijective. It's injective and surjective, but it is not the case that even if going forward it is continuous, that its inverse will be continuous backwards. Okay, and I hope this illustrates the reason why. Okay, it's because of the fact that we can have elements here that are not connected being mapped onto elements here that are connected by a little line. Okay, and then if you were to do the inverse, then it would fail continuity, because we then have elements here that were next to each other being mapped onto something that wasn't next to each other. Okay, so when we defined continuity, we only wanted it to be the case that all of the elements that were next to each other here were also next to each other here. We didn't insist that every element that was next to each other here was also next to each other here. Okay, so it only goes one way. Continuity, we only insist that it works one way. Okay, in the definition of a continuous function, we're only working one way, and that's why you can't say, even if the inverse exists, that the inverse function will necessarily be continuous. Okay, so I hope that example has illustrated that point. Okay, so we'll call it there for this video, and in the next video what we'll do is prove one final theorem about continuous functions, namely that if you compose two continuous functions together, you'll end up with another continuous function.